Good afternoon, everyone, and welcome to another Back to Basics video. If you're watching this on Patreon, thanks so much for supporting me, and if you're watching it on YouTube, you could have gotten this video a week ago if you signed up for Patreon. You don't have to pledge a lot, but any small amount helps the channel. Anyway, self-promotion done. Let's get on to explaining the amp. Now, the SI defines the amp. Very complicated, and it doesn't make a lot of sense, but we'll go ahead and give you the SI definition. I'm going to read it verbatim because it's really weird. Anyway, so SI defines the amp as a constant current which, if maintained in two straight parallel conductors of infinite length, so these extend out forever in this direction and that direction, and if they are placed 1 meter apart, so 1 meter, that's supposed to be an M, there we go, between two straight parallel conductors of infinite length of negligible circular cross-section, so basically infinitely small conductors, placed 1 meter apart in a vacuum, it will produce a force between those conductors, a force equal to 2 times 10 to the negative 7th newtons. That is a very convoluted and very confusing way of explaining the amp. So I'm just putting it there so that everybody knows the SI version of it. I mean, for all I know, you might be watching these videos as part of your studies, and that's what they want you to know. So we'll explain it that way. Now, we'll explain it another way here, where 1 amp is equal to a charge of 1 coulomb per second. This doesn't make a lot of sense yet because we haven't learned what a coulomb is, but we'll be learning about coulombs in the next chapter of Back to Basics. So basically, if you have a conductor and you have current flowing through it, 1 amp is also going to equal, if you select a point, in 1 second, 1 coulomb of charge is going to pass through that point. And we'll explain, like I said, we'll explain coulombs soon, but remember this, because we're actually going to do some fun math involving the coulombs per second a little bit later in the series. Anyway, but we can also go back to Ohm's Law and explain, let's see, yeah, I'll go ahead and erase this, and explain amps through Ohm's Law. Now, we all know that Ohm's Law, V equals IR, correct? So we can also solve for I being current. So I is going to be equal to resistance over voltage. And I use this a lot in my videos when I'm calculating a theoretical voltage through, say, a resistor, an LED, or something. You use Ohm's Law if you have two known variables. You solve for the unknown variables. You can even substitute in other variables. So we can also take P equals IV, and we can also solve for I here. So I is going to equal power, or wattage, over volts. Now, an interesting thing that you can do at this point, I should have saved the V equals IR, and then so I is equal to V over R. We can also substitute values in. So let's say we have wattage and we have resistance, but we don't have voltage as a known variable. Well, we can take IR and we can go I equals P over IR, and then solve that way. you multiply both sides by I, so you get I squared equals power over resistance. That's a terrible R. And then you just continue using your algebra to solve. We can also substitute in, if we don't have resistance, we can substitute in equations solved for voltage and current with regard to resistance, or so on and so forth, just like I did here. Now, if we return to our water explanation of current and voltage, we have a tank of water. And the height of the water determines the amount of pressure at a single point, which determines our voltage. So let's install a valve right here. And if we open that valve, the pressure at this point of that water determines the voltage, because it doesn't matter how wide this tank of water is, the depth of the water determines the pressure, and that's your voltage. So the pressure at this point is our voltage, which, as we start draining the water out, the water level decreases and the voltage decreases because the pressure of the water decreases. Now, the speed at which the water comes through this valve is the current of the water. Now, there are ways we can increase this current. We can increase the current by making the valve larger and therefore decreasing the resistance of that flow of water through the valve, opening the valve further. That will increase the current by decreasing the resistance. We can increase the current by raising the voltage, increasing the pressure. So we make this water deeper and the current will increase. The actual amount of water we have, though, and we'll get into this in the next video when we talk about coulombs, the amount of charge, if we make the tank wider, that's not going to increase our current at all, because the current is dependent on the pressure of the water and the resistance of whatever that water is flowing through. So there's how we tie in our amps to our water analogy. And we'll talk about coulombs in our next video, and at that point we'll talk about amounts of charge when we are increasing the size of the tank. So thank you so much for watching. If you liked the video, consider clicking here to subscribe if you're watching it on YouTube. I'll put a video right here that YouTube thinks you'll find interesting. The Back to Basics playlist will go right here, and a link here for my Patreon if you'd like to help support my channel. So thanks so much for watching, and we'll see you next time. Bye-bye.